So today I'll talk about cybersecurity challenges and solutions for IoT or the Internet of Things. So maybe I'll talk maybe roughly about an hour or so, and then we'll open up for questions in case you have any. All right. So just to get started. So if you look at the history of Internet, it's about 50 years old, and the first time. Back in 1969, when it started, there were only 4 computers in the whole of Internet, right? And most of them were in the west coast of US. And this person that you see here, he is Leonard Kleinrock. He's considered one of the fathers of Internet. And this machine right here, this was a router. It looks bigger than a fridge, but this is how routers were back then. And one of the most common applications back 50 years ago, people didn't have personal computers. So a university or a large organization may have a mainframe computer, and what you would do is you would remotely log into that computer and then execute your jobs. So one of the common applications back then was Telnet, and you would remotely log into a computer using that. And you would first type LOGIN for your login. And in this case, they sent L, and then they sent O, then they sent G, and this is where the whole system crashed, right? So the first time we tried something on the Internet, we survived only 3 characters and everything crashed out. But coming from there, things have changed, and this roughly shows you the evolution of networked computers, and this is a very, very USA-centric view. And then the idea really is that, starting the 80s and so on, Internet evolved and there were many, many more computers. And as the network became popular, applications also changed. So back in the 70s, common applications might have been Telnet. In 1971, 75% of the network traffic was just email. Other applications were like file transfer. We are talking over a voice protocol. So, Microsoft Teams or things like WhatsApp or any other, let's say Skype. What these are network voice protocols, so voice over IP kind of protocols. So these are not new. They have been around for a long time. But it is just that, things where the popularity has changed. And back in the 70s and 80s, most of the users of the network were actually academics, maybe researchers in universities, or in some cases even military and other research organizations. Things changed in early 1990s, because somebody by the name of Tim Berners-Lee invented this protocol called HTTP, Hypertext Transfer Protocol. And as a result, what happened is it became very, very easy for us to find information over the network, right? And since now we could locate information very easily, people started, building web pages for disseminating information and so on. And this in turn led to the popularity of the Internet. So basically, computer networks opened up for the general public. And consequently, other applications came up, for example, Internet-based commerce. So back in the 1999, 2000, 2001, companies such as Amazon, eBay, these things became popular. Another 5 or 10 years down the line, social media, for example, Facebook and so on, they became popular. And in the last 5 years or so, now we have things like shared economy, where things like Uber and other, I can't probably know so many of the Indian ones, but Grab and things like that, they have become popular now. Right? So this is sort of the evolution of the Internet over the last 50 years or so. And there's another way of looking at things. If you look at pre-Internet, when we had just telephones, all the communication was human to human, right? You would pick up a phone and then you would call somebody. With the Internet, and we talked about few evolutions of the Internet. So we had the Internet of content, where things like email or just web browsing was popular. Late 90s, we talked about internet commerce and so on. And more recently, we have social media. no matter what, at least on one side, we had a human involved. So here, both the sides, we have a human. Even if you look at the traditional internet, it's a human who wants to send an email or browse the internet or look at a web page. If you look at internet services, Internet of People, it's again a human who wants a service, or it's a human who's uploading a video or something on Facebook, and it's a human who's downloading the same thing. Right? So at least one of the endpoints is a human. A human decides whether to start a connection or not. But in the last 5 years or so, things have changed. Now our devices have become independent enough, or they have become smart enough so that they can decide when to exchange information. They don't need any human intervention. Just give me a sec. Okay, yeah. So in the last 5 years or so, the internet has so we have devices now which can communicate on their own, and they can decide when to exchange information. They can decide how to process the information, and they can also decide how to act on that information. Right? And that's where we have machine-to-machine communication and the Internet of Things. As a result, for what could happen? So let's take an example of a power grid. Okay. A typical power grid you can think of has 3 components. There's a generator part of things. So that's the hydel power plants or diesel power plants and so on, or nuclear power plants. So these are the ones who are generating electricity. And then you have a transmission network which brings the power usually through high voltage from the generators to the consumers. And at the consumer side, you have the distribution network. Okay. And what you would like, if you're a power grid operator, is to match the generation with the demand, right? You want to do supply and demand management. So historically, how do you know how much demand will be there for power? So we have meters at home, and somebody comes in once every month, takes the meter reading, and then goes back. And of course, you get a bill, but the power grid operator also uses that bill or the meter reading to kind of guess how much power do they need to generate. But as you can tell, this is not very efficient because you get the information at the end of the month, and then the demand can also vary with time, right? So the amount of electric power that we consume, let's say at 6 in the evening or 10 in the morning, is very different than the power that's consumed at 2 a.m. So we cannot do fine-grained control. But now imagine that every house has a smart meter. And what the smart meter can do is it can measure the power in real time, and it can send back readings to the smart grid operator, let's say every 5 minutes or every minute and so on. And as a result, what you can do is you can match your power generation and demand much more efficiently and much more, in real time. So this would be an example of actuation. Actuation means you can step up or step down your generators based on real-time information and monitoring of your system. Okay? So this is one example of how Internet of Things can help us. And then there are many other applications of IoT. For example, in smart cities, you can control, for example, the street lamps based on whether it's dark or not. We have already gone through 3 industrial revolutions. Now it's people talk about the 4th industrial revolution, and in this case, we think that every small piece of equipment in the factory will be connected, and then you can control your processes in a much better way. Right? We can have connected buildings, so where we can look at occupancy levels of the rooms, and based on that, we can decide whether to turn on a light on or off, or you can control the air conditioning settings. Now we have autonomous vehicles. We already talked about smart energy and so on, right? So there are many, many different applications of IoT. And currently, smart cities and connected industry seems to be the most popular. but things may change over time. And here's another graph which kind of tells you what we expect in the industry, what kind of technologies we expect to have the biggest impact over the next 5 years or so. And you can see IoT is expected to have a big role in terms of how our industry, how in terms of the dollar value and what kind of impact it will have. Now, this is all very good. So we see that there are many different industries or verticals taking up IoT technologies. And we also see that IoT has the potential to have a lot of financial or economic impact in the society. But then there are certain concerns which people have before they employ IoT, right? Especially if you're a CTO or CEO of a company, and if you're thinking that, do I want to switch over to IoT-based technologies? Then you do a cost-benefit analysis and see, okay, how much am I paying and what do I expect? Are there any risks associated with this technology? And when that happens, one of the things you consider is, what is the risk? One risk is security. And when you look at the news and things like this come up, then you get a little bit more concerned before you decide on adopting IoT. So these concerns, security concerns, the biggest example that you will see has to do with the Iranian nuclear power plant. And in this case, some adversaries, we don't know who, nobody claims, they infected the nuclear power plant in Iran with a worm, with a virus. And as a result, there was a lot of equipment damage in the power plant. And some people think that that pushed back Iran's nuclear power program by about 5 to 10 years. For example, so this is Stuxnet was about 10 years old. More recently, about 5 years and 4 years ago, both in 2015 and 2016, Russia and Ukraine got into a fight over a certain region called Crimea. And Russia came in and annexed that part. So Russia and Ukraine had a fight. And then Ukraine claims that Russian hackers got in and they were successful in turning off power in a couple of regions in Ukraine in the middle of winter when they need electricity for heating and so on. And this happened in 2015 and again in 2016. Other examples, so this is in the US. So Lansing is a city in Michigan in the US. And in this case, hackers got in and infected all their, so this is the land and water department. And in this case, the hackers got in and infected their computers with ransomware. And as a result, their operations were affected. And the last example that I have is related to Saudi Aramco. So this is a company with one of the biggest companies in the world in terms of market valuation. And this is the biggest petroleum producer in the world. And around 2013, again, they got hacked. And in this case, the attackers, they killed their hard disk. They physically crashed the hard disk and wiped out all the data. So as a result, their operations were affected, and then they suffered billions of dollars in losses. So these were examples that I have. These are much more, industrial in their scope. And if you're thinking about, regular IoT devices that we think of, the sensors and other things that we may employ in our houses and our offices. So there's another example, and this was something in, I think, 2017 or so. And this was a botnet attack, and the name is Mirai botnet. And what they used is they used regular IoT devices such as webcams and so on in order to launch a distributed denial of service attack. So in a denial of service attack, what we do is we pick let's say a victim, maybe a server or a computer that we want to attack. And then we start sending so much traffic, so many requests or data to it. So one of two things happen. Either the connection that goes to that server, the network connection, it's overwhelmed with traffic, and as a result, legitimate customers cannot get to the server, or the server starts processing so many requests that its CPU and its memory, they can't handle it anymore, and as a result, legitimate customers, when they try to access the server, they can't get in. And in this case, they attacked something called a DNS server. And what DNS does is it does the translation from names to IP addresses. So for example, for humans, when we want to access a website, we remember like www.amazon.com. But computers don't really use this Amazon.com. They want the 32-bit or 128-bit IP address. So DNS servers do this translation. But if I ask you go to Amazon.com, you can write www.amazon.com, and then your web browser calls this DNS translation, and then that will translate the IP address, and then the actual TCP connection that goes out from your machine is based on the IP address. Now, if I somehow can disable all these DNS servers, then you will not be able to do the translation from host name to IP address, and then you will not be able to access the internet, essentially, right? And that's what they did. They attacked this service called DIN, and DIN provides DNS service to all these quite popular websites and services, including Reddit and Amazon and PayPal and so on. And as a result, none of them were accessible for over a period of time. And, consumers were affected because they could not get to these services. And these companies themselves had to suffer financial losses, right? Because they didn't get the business. And if you look at the way things worked, very quickly, the owners of this botnet, they would first somehow infect let's say a webcam. Once it's infected, they had a report server. So this webcam which is infected now would send back a report to this report server saying there's a new victim, there's a new bot that has been recruited, right? And then the attacker had two other things. There's a command and control server, and then there's a loader. What this command and control server does is periodically it goes to the report server and sees, do we have any new victims? Once it finds that there's a new victim, it will now send a command to infect, and it sends it to the loader. The loader has the actual binary for the malware, and then it will send the binary to the bot victim. And on the day that we actually want to launch the denial of service attack, we send the command to the victim, and then the victim actually now starts sending the data to the target, and now we are all infected. So now this is the whole process, but the whole thing, it began with identifying these victims, right? How do I get into one of these IP cameras, right? What is the easiest way of getting this? Did they use some very, very smart exploit to get in, and then they were able to hack into these devices? Turns out, no, it wasn't very, very smart. So this is one of the examples of the IP cameras that was hacked into. It turns out that when they shipped out these IP cameras, the default username was root, and the default password was XC3511. So if I have this camera, and if I know that my friend has a similar camera, then I also know what is the username and the password for this camera. So in many cases for IoT devices, they come hard-coded with these username and password, and either the users are very lazy and then they don't change these usernames and password, or in some cases IoT devices are, they're not very user-friendly. So you don't even have the option of changing the username and password even if you want to, right? So they may be hard-coded into the firmware. So in this case, if you look on the internet, you can actually get large lists or dictionaries of usernames and passwords. And then you can do a dictionary attack. So basically you go through the list and try username, password, does it work? And then hopefully, if you're the attacker at least, you hope that one of the username passwords in the list will work. So this is one way. And then there are other also examples of IoT devices being hacked. So this is similar to what we were talking about, somebody hacking into webcams. There are examples of people hacking into cars. And then there are examples of people hacking into all kinds of embedded devices and so on. So this is starting to become a very tough problem and an important problem. So that was sort of an introduction to why security is important for IoT. And now what I'll do is I'll move into talk a little bit more about what does it mean when we talk about security for IoT, and what are the challenges and the difficulties in securing IoT systems. So in general, for a traditional computer system, when we talk security, it usually means this, what is typically called CIA, confidentiality, integrity, and authentication. So confidentiality basically says, when I send something on the network, only the receiver should be able to understand what are the contents of the message. Anybody else, even if they get their hands on the message, they should not be able to understand what's written in there, right? And usually we will do this through encryption. Integrity says, if I send a message on the network, nobody should be able to change the contents of the message, or even if they change it, I should be able to detect, right? So this is usually done, for example, with the use of hash functions or message authentication codes and things like that. And authentication says, you want to verify the identity of the person on the other side. And typical ways of doing this is through username and password. So we do need all of these for IoT also, no change. But then there are changes in the way these, so I gave you some examples of protocols, right? So for example, we use MACs, and for encryption, we may use something like, let's say DES or SSS or AES. So these are all encryption protocols, right? So those protocols exist, but if we want to apply them directly for IoT, there is a problem. Why? Because these existing protocols that have been developed, they have been developed primarily thinking about laptops, desktops, or smartphones. And these devices have pretty powerful processors. They have a reasonably good amount of memory. And then energy or the power is not a concern, right? Desktops can be plugged in, and your laptops and your smartphones, you can always recharge. But if you think about IoT, they don't have the latest Intel core, quad core or dual core processors. They have a very, very basic microcontroller maybe, right? And they are probably charged, they're probably powered by a battery, maybe a coin battery or maybe a AA or a AAA battery of some kind. And you want the device to last on that battery for many years. You don't want to go every day and change the battery. So traditional protocols consume a lot of CPU cycles. They're computationally intensive. And if you run them on IoT devices, you will run out of battery very, very quickly. So essentially what you need is very lightweight solutions, which are computationally not that intensive. You can execute them very easily, and you won't consume too much power. And that's one challenge. Another thing that we have to worry with IoT is privacy, right? Your phone has many sensors. In some sense, you can think of them as IoT devices, right? And other things, maybe, other IoT devices we think of could be cameras or other things that we deploy along the roadside. So this is one example. In this case, this is a trash can, right? A garbage bin where you can throw your waste. And this is somewhere in London. And this guy was equipped with a Bluetooth and Wi-Fi. And the idea was, if the bin is full, it can send a message saying, full, please come and clean. But this Bluetooth also tried to pair with every nearby passenger. Anybody who's walking, the Bluetooth is always scanning, and it will know if you were in the neighborhood, right? And if that happens, as you're walking along the street, you cross this trash can, you walk 100 meters, there's the next one. And then, the next trash can will also track your phone. And as a result, I know where you go, where you went at what time and so on. So there are all these privacy issues, right? Even other things, your smartphone, when you're using Google Maps, right, it's quite useful because it tells you which way to take. It also tells you how much traffic there is, but it's also using your data. It tells where you are, and it tells how long you take to cross, to go along a street, and Google Maps then builds up on top of that. Then Google actually knows where you are at a certain point in time. Whenever you're using Google Maps, Google knows where you are. So then it leads to privacy concerns, right? And this data that you give to Google Maps, who is the owner? Do you own it or Google owns it? Probably when you first signed on to, when you first went to Google Maps, maybe you clicked some accept, and probably Google owns it. But then we can always argue about it. And then another big thing, and this is something I will talk about later today, is physical security. When we think about our laptops and desktops and phones, we think that they will always be with us. Sometimes phones can be stolen or other things, but we still think that we are the only ones who will ever get access to the phone. But if you think about IoT, maybe you have deployed an IoT device by the roadside. Anybody can come and steal it. And if they have stolen it, you don't have physical security anymore. And this can also lead to security challenges. And in just 5-10 minutes, when we get to that, I'll talk about this in a bit more detail. And then, why are IoT devices targeted? Some things are, because of the value of the data. And sometimes it's because that IoT devices are, generally a bit more easier to hack into compared to your laptops and phones and desktops. So one thing is IoT devices are usually always on. You don't turn them off. So for example, right now I'm on my laptop. As soon as this is over, I'll shut it down. Once I shut down my laptop, nobody can hack into it because it's off. Right? So the time period over which my laptop is available for being attacked, it's a few hours a day. But if the IoT device is always on, it's anybody can try and get into it. Right? And with IoT devices, manufacturers, try to make it easy to use. So if you try to sell an IoT device, and once I buy it and I take it home, if it requires a complicated setup process where I have to give a username, password, re-enter the password, many people may not be happy. Most of the audience here is either electrical or computer engineer and so on. So maybe for us it's okay, but if I think of my mother, she's not going to be interested in putting, username and password in the IoT device. That's not going to work for her. Right? And if you think about my laptop, I know in general how it should perform. But if occasionally I see that my laptop is the fan is always on, or it's becoming too hot, or if I see that it's running very, very slowly, then I get suspicious. Why is my laptop so slow? And one of the reasons is probably it's running something. It's being used as a bot, or it's running some malware. And then I get suspicious, and then I use an antivirus to check if something is wrong. Okay? IoT devices don't have that. You install a device and then you forget about it. And even if they have been hacked into, we usually don't know. Right? And then IoT devices, there are many IoT devices. So if I hack into one, possibly I can use them to launch denial of service attacks and so on, and things like this. And I'll also give you some common vulnerabilities hackers use to get into IoT devices. So this is one example of an IoT device where we have taken off the case. And if you take off the case and if you look at the PCB, you will see serial ports like this. These are open, they're not being used, but they are in the PCB because when the IoT device was being developed, this was used by the developers for debugging, for checking the signals and other things. once the device has been developed, you don't want to redraw or redesign the PCB again, so you just leave it as there. But if you open up, you can now solder in some wires here, and then you can connect. This acts like a serial port, and now you can read anything in the device. Right? So that makes it easy to look at the memory of the device and anything else that's going on. In terms of other vulnerabilities, so with this we talked about when we were talking about the Mirai botnet. In many cases, devices come with weak and hard-coded credentials or username and password. In many cases, your IoT device collects the data, but then it uploads the data to a web server, right? Maybe it's in the cloud or something. What about these applications that you're using to visualize the data or to access this database? Are they secure? Maybe, maybe not, right? If there are vulnerabilities there, then you can get into trouble. Even the network communication. Right now, if you go to a website, especially if it's a banking website and so on, you will see that the protocol that you use is HTTPS, right? Not the traditional HTTP, but HTTPS. So this S is for secure in the sense that all your data is being encrypted. But if you try to encrypt everything in an IoT device, encryption costs energy. So your device will run out of battery very soon. So in many cases, we don't really use secure network communication. And as a result, your IoT device may be vulnerable. And another thing might be, every few days or so, if not days, maybe every few months or so, you will see that you get a patch from Windows or from Android or iOS saying that there's something, and then you need to apply this patch to update your software. So they probably found some vulnerability and the patch is there to fix it. And when these patches come in, they usually have an integrity and verification saying that this was created by Microsoft or this was created by Apple. And once you have verified the signature, then you know that it's coming from a trusted source. And then you feel okay that, all right, fine, I can install it. But many of the software that comes in, firmware and other things for IoT devices, they don't really have this integrity and verification checks. So it's quite easy for hackers to send in malicious code, and you will install it because IoT devices don't do integrity and verification check. And that's if you're getting these updates and patches. In many cases, IoT devices are manufactured by small companies. They may not even bother to update their operating system and the firmware. And vendors will not support, even if there's a vulnerability, vendors don't usually care, small companies. And then can be coding errors and then physical vulnerabilities that we were just talking about. And then these are the reasons why somebody the additional security challenges. Sometimes the data that the IoT device is generating is quite valuable, so that makes it attractive to the attacker. There are a large number of identical devices, so that makes it easy to attack. If you're hacked into one, it's very easy to hack into others. There is no user interface, so the user doesn't check that often, and then limited computing and battery power and so on. So now let's shift gears a little bit, and now let's talk about what it takes to secure an IoT system. So some of the things that we need are very, very similar to what is needed for traditional computer systems, right? So since IoT devices are generating data, and probably these data are being stored in the cloud or somewhere else, data center, we need mechanisms for controlling access to the data. Just like we do for traditional systems, we also need similar things for IoT. Another big thing is establishment and management of trust. Who is responsible for creating usernames and passwords? Who is responsible for revoking these, right? And we want to do this in a distributed and a very, very efficient way because, if you think about your university, maybe it has a few thousand students and employees. Compared to that, a typical IoT installation may have tens or thousands or a few lakh IoT devices being deployed. So the scale is very different. Right? So you want to do these things much more efficiently. And then we were talking about protocols used in data transmission. So we have to move towards more use of secure protocols. Your phone and your desktop may have antivirus and firewalls. Right? Most Windows devices and most Android devices have firewalls and antivirus software, but IoT devices may not have. So we need to go towards that. And we need to make patching and updating of software on IoT devices much more easier compared to what it is right now. And to achieve all of this, if you think about an IoT ecosystem, there are many players. There are the people who write the apps. There are people who make the devices. There are people who operate the cloud platforms over which you collect data and so on. And then there are all other players in here, right? Everybody has to come in and play their part. So everybody who's either developing the code or running the platforms that are being used by IoT devices, of course, they have to use or they have to design the components in a secure way. In addition, the government and the policymakers and the regulators, they also have to come in and play their part. Okay? So only when everybody comes in and they work together, that's when you'll have security for IoT. And of course, as a user, there may be firewalls available, there may be antivirus software available and so on. But as a user, if I don't pay attention, if I don't install them, if I disable them, it's no use. Right? As a user, if I don't choose hard passwords, if I say my username is username and password is 1234, then the effort of all of these, that's wasted. Right? As a user, also we have responsibilities and we have to make sure that we play our part. Okay? So this part was more or less about general talk about what's security for IoT, why it's important, and what are some of the issues. In this part of the talk, what I'll do is I'll change a little bit, and I'll talk about more from a solutions point of view, and more from a bit of a research point of view, where we will take a look at one specific security challenge for IoT and how that can be solved. And in this case, we would like to look at physical security for IoT. Right? So some time back, we were talking about different security challenges. I said physical security is a problem for IoT because many IoT devices may be deployed out in the open. So you can deploy sensors, let's say, for traffic monitoring, environmental monitoring, and so on. And these will be deployed in the open. And if there's a thief, they can steal the device, put it in their pocket, and walk away. So why is this a problem other than the fact that now you've lost an IoT device? Why is it a security issue? Right? So think about authentication. When we were talking about authentication, we said the typical way of doing authentication is username and password. So for example, when you check your email, let's say it's Gmail or whatever it is, your university email, you go to the website, it asks for your username and password. And for us as humans, we remember our username and password in our brain, right? So the brain is our memory, and we remember username and password there. What about an IoT device? In an IoT device, there's no human sitting and trying to enter the username and password every time it wants to access the network. So we have to store the username and password in the device itself. So where can we store? In the memory, right? We have to store the username and password for the IoT device in the memory of the device. So if the username and password is stored in the memory and somebody has stolen this device, then what we can do? We can open up the device, and you remember the picture that we just saw here some time back. I can connect a few wires here. I can connect a few wires and then I can try reading of the memory. Or I assume that this is the memory chip. I can take this out and I can try reading the contents of this memory chip. Right? And when that happens, I can gain, I know what the username and password is. So I can connect a LED to access the physical port. And these are not the only way. If I have access to a device, if I have stolen your IoT device, I can let it operate normally. But what I can do is I can subject it to side channel attacks, contactless attacks. So what for, just as an example, I could place an antenna just on top of your processor. And while your CPU is running, what happens, it's drawing current and so on. And the CPU will actually emit electromagnetic radiation. So my antenna can pick up that electromagnetic radiation. And what I can do is I can look at the behavior and I can crack what your username and password is. What is your password you're using? People have already demonstrated that. Right? So these are all kinds of attacks which are possible. So then what is the solution? Right? So the solution would be that I don't want to store anything in my IC, in my memory. So I don't want to store anything in the memory of the device. There's no human who's going to go there and enter the username and password. So what else can we do? Then we think, how else do we authenticate ourselves in real life, in human life? So for example, in India, you have the Aadhaar card. And with the Aadhaar card, there's a database that has your fingerprints and even your iris scan in there. And if you go from abroad and you take a flight and you come into India, one of the things that they will ask you at the airport is, you have to put in your fingerprint. So one way of identifying a human is through his or her fingerprint. A fingerprint uniquely identifies a human. So then the idea is that can we design something like that for our semiconductor devices also? Right? Can we somehow give them, or can we exploit something that happens in ICs and semiconductor that is equivalent to giving them a fingerprint that we can use for identifying and authentication purposes? So that's where our research comes in. And here we are trying to use hardware security primitives. Basically, we are trying to use properties of the hardware itself in order to help to authenticate the device. So how can we have these hardware fingerprints? So to get hardware fingerprints, we use something which are called physical unclonable functions, or PUFs. And what a PUF does is it exploits things that happen while we're fabricating the IC. And as I will show you in just a bit, during the manufacturing process of an integrated circuit or an IC, you go through a number of steps. These are highly controlled steps, but still, since the wires and the other things in a typical IC these days are so small, we cannot control them precisely in the order of nanometers. And as a result, every IC is actually unique if you look inside it. They may be the same IC, they may be the same Pentium chip, they may be the same, in my student days, we used to have logic gates as ICs like 7074, 7072 and so on. They may be the same IC, but internally, if you zoom in with a microscope, you will see that there are variations, there are differences. No two IC is unique, and we will try to exploit that. So let me show you how that. So for those of you who are not familiar with a semiconductor manufacturing process, so this is what typically happens. You will start off with a silicon substrate, right? And you want to build a circuit on top of this. So you will first put a masking film on top, and then you will put a photoresist, and then you take your mask, which is basically a negative of the circuit that you want to etch on this device. You place the mask on top. So in this case, what we are trying to do, let me clear this. In this case, what we are trying to do is a very simple example. I want to create two wires like this on top. Okay? So I will put on a mask here where wherever I want the wire, that part is darkened, and wherever I don't want the wire, there is no mask in there. And then we shine some ultraviolet light on top. Right? Then the ultraviolet light reacts with this masking film, and later on we take out the mask, and then we go through a process which is called etching. And once we do the etching, this part of my masking film can be removed. And ultimately, I'll be left with these two wires. Right? That's the semiconductor manufacturing process. But it turns out that we cannot control exactly our etching process or the way the mask is placed or the way the ultraviolet lights are being shined on this. And as a result, there'll be some variations. So think of this as a gate that we're trying to manufacture, right? And if you think of a gate, and then there might be an interconnect between that. Now, how much time will it take for me, if I think in terms of the circuit delay, how much time will it take for my signal to go through a gate, through the interconnect, connecting the two gates, and then pass out? So the circuit delay would depend on the interconnect delay and the gate delay. And the interconnect delay would in turn depend on the length of the wire. And the argument I'm trying to make here is we really cannot control the length of this wire in the order of nanometers, 1 or 2 nanometers. There will always be some variation. Right? Just as an example, this was the layout that we had in our mask. And if you see here, these wires are very, very nicely drawn out. There are 90-degree angles and so on. But after the whole thing is done, if you look, the edges are not 90-degree anymore. This thing was a nice little rectangle. This has become a circle and so on. Right? And whether it's a whatever technology you're using, there will always be some variation or the other. Right? And people have shown, for example, just as an example, if you see, if you are going for the 130 nanometer technology, if you think that your ideal gate length is 90 nanometers, usually we will see that there is a variation of about 5.3 nanometers. The design accepts that there will be a variation like that. Right? And in the 45 nanometer case, we'll have a variation of 2 nanometers. Right? These are always there. And then what we say is we can exploit these naturally occurring variations that occur during the manufacturing process and use this to create a fingerprint for a semiconductor device. Okay? Let's look at how that can be possible. So look at this example circuit below. What we have is we have a flip-flop in the end. And in this flip-flop, the way things are organized, if the D input comes first, it will register a 1. And if the G input comes first, it will register a 0. Okay, so flip-flop part is fine. And what we really have is 2 rows of multiplexers. There's a top row, there's a bottom row. And our signal that goes into these multiplexers is actually like this. There's a top path, there's a bottom path. And for each of these columns of multiplexers, we have a control signal or the selection bit right here. So in this case, I select the 0 input for both the top and the bottom multiplexer. Here I will select both the 0 inputs of the top and the bottom. Here I'll select the 1 input of both the top and the bottom multiplexer. Okay. And if you look at the way things are organized, the blue input goes to this and the red input goes to this. Similarly, in the next stage also, the red input goes here and here, and the blue input goes here and here. Okay? So you can see that this is the order. So now let's see what happens if I give this particular selection bit. Okay, so if I give 0 here, this is selected and this is selected. So let's see what will happen. For the top multiplexer, the signal will come like this and this is coming out. And for the bottom multiplexer, since 0 is being selected, we will get a path like this. Here again, I'm selecting input number 0. So this will be selected and this will be selected. So the path of the signal going out is like this. And in the end, input number 1 is being selected. So this and then this. Okay. So at the end, we have two signals coming to this flip-flop. The blue and the red. Okay. So there are two signals coming into the flip-flop. And at least on this design, the blue path and the red path, they're identical. There is no difference at all between them. Okay. And if I give a clock pulse here, ideally both should come here at the same time, right? Because they're going through identical multiplexers. They're going through wires which are identical. So the blue path and the red path, the top path and the bottom path here at the input of this multiplexer, they should happen at the same time. But like we just said, when we try to manufacture these wires, there'll be some random variations. So even though in my design phase, everything was supposed to be identical, but maybe the blue path is a little bit shorter than the red path. Maybe the red path is 1 nanometer longer. If the red path is 1 nanometer longer, then the blue path is shorter, so the blue signal will reach first. Okay? And my output will be 1. Now, if you were to take this same circuit and rebuild it again, will it be the same? Will this path still be 1 nanometer shorter? Most likely not. We don't know. How is this 1 nanometer shorter? Because randomness. During the manufacturing process, maybe during etching, we etched this one a little bit more. So if I do the same thing tomorrow and I do the etching, maybe this wire gets etched a little bit more. So we cannot control this. No matter how hard you try, we cannot control. So you repeat the same process again every day, you will get a different answer. Even on a same silicon die, different ICs, same design. In some cases, maybe this is a bit long, this is a bit short. In some, maybe this is long, this is short. We cannot control, right? So this will come up with a random thing. And in this case, what I had is, I had a number of bits to control. We call that the challenge. And this output bit, we call it the response. So here I can have an n-bit challenge and a 1-bit response, but I could take the same thing and create many parallel versions of this. And each of those will give me 1 bit of response. And if I have m of these here, I can get an m-bit response. Right? So I can generalize this. And this is what is done in a puff. You give a certain challenge, you will get a certain response at the output. If you give the same challenge to another device, it's the same circuit, but because during manufacturing things were random, you will get a different output as the response. And that is what I'm trying to show here. Let's say I have 4 different ICs. They have the same perf circuit in there, and we give all of them the same challenge. Because of their randomness in the circuit, they will all give me different responses. And this essentially becomes a fingerprint for this device. You give the same challenge, you get different responses from different devices, and each of those different responses is basically corresponds to a different fingerprint from each of these departments, from each of these ICs. So then what we can do is, if our semiconductor devices come equipped with these puffs, in my research group, what we do is we try to use these puffs and then build security protocols around them. There are certain advantages to puffs. So for example, it's, nothing is really being stored here. So this is not a memory where you are storing username and password. So even if they are stolen, you don't leak any username and password. So that was one of our concerns. And then, we were also talking about side channel attacks such as power monitoring, electromagnetic attacks, timing attacks, and so on. These become a little bit more difficult to do with PUF. So these are certain advantages. So what I will do is I will walk you through one example of a protocol, security protocol, that's designed based on PUFs. And in this case, this is a mutual authentication protocol. And what we are trying to do is, so let's say I have a number of IoT devices, and then there's a data center or a cloud-based server. The IoT device would like to authenticate itself with the data center before it's allowed to upload the data or access resources in the data center, right? And in this case, what I'll assume is each of these devices has a PUF. So if this device has a PUF, I can give it a challenge, I will get a response. If I give it a different challenge, I will get a different response, right? So we can have a number of different challenge response pairs. So what we will assume is that, I'll skip all of this. So what we will assume is that during the installation phase, right, we know one pair of this challenge response pair, and that is stored in the data center. So for each of these devices, we'll have to store one challenge response pair for the device. And just like your email server has to remember your username and password, what we will do is we will store at least one challenge and one response for each device in here. And we can keep updating this challenge response pair every so often, so that so that we are secure against replays and things like that. All right. So now this is the security protocol that we have, and essentially it goes in 3 steps. So it's a bit small in this figure. So what I'll do is I'll walk you through each of those steps in a bit more detail. Right. So this is the first step. So let's say device A wants to authenticate itself with the server, right? So what it will do is it will send its identity saying I am device A. I want to authenticate myself. And if you're familiar with security protocols, to ensure freshness and so on, we usually use a nonce, right? So this is a nonce that I'm sending. So now when the server gets the request, it will look up its memory and say, okay, where is device number A? And then you remember we stored a challenge response pair in the memory. So it will read the challenge response pair. And then it will generate its own nonce. And then it will send a message back to the IoT device. But it's going to encrypt this message using RI. So when you encrypt something, you need a key, right? For example, AES or DES, anything you want to encrypt, you need a key. So essentially the key that we are using is the response that we have stored. Okay? And now I send this encrypted message back to the IoT device. This part is encrypted, and I also tell the IoT device what is the challenge. Now any adversary, any hacker can see what's the challenge, no problem. But in order to decrypt this, they need RI. How to get the RI? You need to have the PUF. Who has the PUF? Only the device has the PUF. So the device will pass the challenge through its PUF, get the response. And then it can use this response to decrypt this message. Nobody else has the message, has the PUF, so they cannot use this, right? So that's essentially the whole idea about the authentication protocol. And then the rest of the things, they're not that important, but I'll just talk about it anyway. We said that we don't want to reuse the same challenge response pair again and again, because at least the challenge is in plain text so people can see, and maybe over time that leaks something.
Sir,
so, yeah.
Sir, just one doubt in this question.
Yeah.
Just one part, because the critical issue.
Yeah, please go ahead.
Yes, sir. If the existing protocol that you are discussing, if any modeling attack happens in this protocol, how can we prevent in this? Yes.
Right.
And one more is that if a single pair of challenge response is leaked, then can it will not hamper the entire protocol execution? format?
So the way this is working, so let me answer your question. So this is one round of authentication, right? I sent my ID and nonce and so on, and then the server encrypted using the response and sent it back. And on the IoT device side, I have to pass this challenge through my perf, get the response out, right? And then I verify everything, and then the authentication is done. But the next time I want to authenticate, I will not use the same response and the same challenge again. So the device creates the challenge and the response for the next round of authentication, and then it sends it back. And when it sends it back, it's still encrypted in this, right? So next time I do this, I will not be reusing the same thing. I will not be reusing the same challenge and response. So that will help me. Okay. So now the question is, what if for whatever reason, somebody figured out what is CI and what is CI is easy enough because it's going on the network in plain text. What if somebody could guess what is RI? Is that a problem? And especially since you mentioned that modeling attack or machine learning based attacks. So usually for that, if you have a strong perf and the number of bits that you're using in the perf is large enough, a single leaked challenge response pair is not a problem. Okay? If for whatever reason you could figure out one of these, it's not going to make any appreciable difference. You will not be able to build a model using just one challenge response. If it's a weak perf, yeah, you're in problem because a weak perf anyway has a very, very limited set of challenge response pairs. But if it is strong perf where the set of challenge response pairs is quite large, leakage of one is not a problem. Okay. All right. So now continuing on, and hopefully that has answered the question. So these new challenge and response pairs which the user has generated, it will be communicated back to the user, again encrypted. So now once the server gets this message, it can decrypt the message using the past response, and then you can pass it through the hash to get the new challenge. And now you will delete the previous RI and CI, and you'll update your memory with the new challenge response pair. So next time the device wants to authenticate, it needs to use the new challenge response pair. So now, anytime you have a protocol, you want to make sure that the protocol is working correctly. And the few things that you would look for are things like completeness, that the protocol accepts all the valid inputs and so on. That it's free of deadlock. It will not enter a state where it cannot get out and it will stay in there indefinitely. We don't want it to get into an infinite loop kind of situation. We want to make sure that it terminates and so on. And then usually the way we can do this is through using finite state machines and then showing that the thing will terminate and so on, right? So I am not going through the proofs here, but just to give you an. So essentially what we do is we do a reachability analysis and then see that when you start at something, ultimately the protocol will terminate and reach the initial state, and then you can re-execute the whole thing and there are no deadlocks and so on. The other thing that you want to in the verification process is you want to make sure that whatever things that you're exchanging, for example, the session keys or the challenges and the response, it should be a good shared key. That means only ID, the device A and the server should know. And then again, there are formal ways of proving that this will happen. So I'm just showing this for the benefit of maybe the research students who are there, just to make the point that if you're trying to get your paper accepted, make sure you have your proofs like this in the paper. That's the only reason I have this. Now, to end, what I would like to show is some actual results based on implementing these puffs and these security protocols. So I am not a hardware person, so I don't make these ICs or I don't make these puffs. But I have a colleague here who is an IC design person, and he specializes in the design of puff circuits. So we collaborate and then we come up with a we came up with a chip design where, he took our protocol and he implemented it, but then the actual part about the puff that was implemented and so on, that's his department. And in this particular, I showed you an example where we were using challenge and response pairs, so they essentially act as the key in some sense. What we also wanted to investigate is that what is the trade-off between the energy consumption and the size of the puff, how many bits that we're using in the puff. Of course, if we use larger bit sizes, if we use a larger puff size, our challenge responses will be longer and it'll give us better security. And also it'll give us better security. Since somebody asked the question, it will help us against machine learning or modeling attacks also. But then if you use more number of bits, you pay the price in terms of energy. Right? So it will. So then the question is, what is the trade-off? How much energy do we need when we use longer ones? So these are some numbers that show, how much energy it costs. So for example, when you have a puff, the energy consumption is actually very, very low. If the order of 100 femtojoules per bit. But on the other hand, if you look at the wireless part of things, when you are actually transmitting the message from the IoT device, the energy that you consume is about 6 times or 5 times, 5 orders of magnitude higher, right? And the other things that you need to do, for example, the error correction and the crypto core, that's about 3 orders of magnitude or 4 orders of magnitude higher. So this is a graph which shows how much energy is consumed by the CPU when we use different key sizes or the puff sizes, right? And each of these has 4 bars, and these correspond to the payload size. So basically how much data is being generated by your IoT device. Of course, if the payload size is higher, we expect to see higher energy consumption. But this also shows you how much the energy consumption increases as a function of the key size or the puff challenge response size. And this is just the energy part from just the radio. Okay? Of course, if you use larger key sizes, so you have to send larger response and challenges, so that will consume some additional energy. But of course, if your payload, the data part is higher, your payload will also be higher. The energy consumption will be higher. So that's what this figure tends to show. Now, while I tried to give you some, I tried to highlight the positive aspects of puffs, there are also certain issues with puffs. One of the things that I want to highlight is, I said you give a certain challenge, you should get a specific response from the puff. And in our example, we were saying that the difference comes in because the lengths of the wires are different in the top path and in the bottom path, right? If I go back quickly. In this case, the difference was because I said this path is 1 nanometer shorter than this path. That may be the case, but what if the device is running for a while? And if you've ever touched your processor, you will see that it's quite hot because of the energy dissipation. So when the device heats up, we all know from thermodynamics that if you heat something up, it will expand. So then the chip also expands to some extent. And if you heat up, maybe this one expands a little bit more than this. So then the bottom path may be shorter than the top path. And if that happens, now for the same challenge, you may end up with a different response. Right? So most of the puffs, they are actually sensitive to operating conditions. And if the temperature increases, for example, you may get a different response. In order to fix these, most of the puff circuits, in addition to the puff circuit that you just saw, they will also have error correction codes in there. But then, sometimes they'll be able to fix it, sometimes they will not be. Or if you want to really have very, very low error probability, you have to invest in fancier error correction codes. And that leads to cost in terms of, semiconductor cost. And then the other thing that somebody was just talking about was modeling attack or machine learning attack. So over time, you see different challenges, and maybe, let's say you have some guess about what the response functions are. So you can feed it to a machine learning algorithm, and then this machine learning algorithm can probably build a model for the puff. So now, if you give it a challenge which has never been seen before, you feed it to this model, hopefully the model can predict what the response would be. If the model is successful, then you have lost your security properties. Right? But then, security is always a cat and mouse game. So sometimes you win, sometimes the attacker wins. So once people have figured out that there are machine learning attacks, they're possible. So designers are also trying to come up with counter mechanisms for this. So for example, they talk about reconfigurable puffs, where you reconfigure the whole puff and the previous model is not valid anymore. So these are all ongoing research challenges. So just to conclude, hopefully, yeah. So what I wanted to highlight in this talk is that IoT presents us with a number of security challenges, and we need coordinated efforts by all the stakeholders before we can come up with solutions to this. And there's ongoing research in many different directions, and one possible way is looking at these hardware-based security solutions. Okay. So thank you very much. So that's my presentation. So if